discussion of rational functions today. Last class, we studied the behavior of two new parent functions, 1 over x and 1 over x squared. And we can graph many rational functions by transforming one of those parents, shifting it around in the plane. But you can't graph every rational function that way. So today we're going to learn some more techniques for graphing rational functions. Remember that both of these parent functions, 1 over x and 1 over x squared, had a vertical asymptote at the value of x that's excluded from the domain of the function, which was 0 for both of those. So in both of these pictures, you see a vertical asymptote that is a line that the graph gets close to but never touches. All right, so here's some sort of frequently asked questions about vertical asymptotes. So question 1, how do you find the vertical asymptotes of a rational function? They happen when the denominator equals 0. That's how you find vertical asymptotes. They happen when your denominator equals 0. How does the graph of a rational function behave near a vertical asymptote? It either gets really big or really small as it approaches the asymptote. So these are the sort of the 4 pictures you can have. You approach x. Yes, for a vertical asymptote, it will always approach infinity or minus infinity. Yes. So as x approaches a, which is the location of the asymptote, from either the left or the right, the function will either blow up or go down to infinity. All right, how many vertical asymptotes can a graph have? Yep, it can have 0, right? You can have a rational function that has none. You could have 1, and you could have many, right? All depends on how many x values make your denominator equal to 0. Can you identify the equations of these vertical asymptotes? So maybe let's look at this first graph here. What's the equation of that vertical dotted pink line? What is 2? X equals 2. Yeah. Every point on this line has an x coordinate of 2. Every point is 2 comma something. So the equation is x equals 2. All right, how about the leftmost pink line in this picture? X equals -2, and this one would be x equals 2. Good. Yes. How many values of x make the denominator equal to 0? Right, so to find vertical asymptotes, that was the first question. Your rational function is p of x over q of x, a polynomial over another polynomial. And you get vertical asymptotes when that denominator q of x equals 0. So however many solutions there are to this equation, that's how many vertical asymptotes you get. So it's possible to have none, right? It's possible to have 1 or more. All right, can a graph of a rational function ever intersect a vertical asymptote? Nope. The function is not defined at that value, so it can't ever cross it. How do you indicate a vertical asymptote on a graph if you're drawing a picture? Dotted line. Yeah. Because it's not actually part of the graph, it's just a line that helps us draw the graph, so we make it a dotted line to say this isn't part of the graph, it's just helping me draw the graph. All right, question 7. Is there anything else I need to know about vertical asymptotes? Yes. A value where the denominator is 0 does not always result in a vertical asymptote. So I lied to you a little bit in the first question. I said vertical asymptotes happen when the denominator equals 0, right? Places where the denominator equals 0. But there is one exception, right? If the x value that makes the denominator 0 also makes the numerator 0, then you actually just cancel those factors and you end up with a hole in the graph at that x value instead of a vertical asymptote. So this means that your rational expression wasn't in lowest terms and you can factor it and cancel. So here's an example. So if I have the function x squared minus 9 divided by x plus 3, what values will make this denominator of this function 0? Negative 3. So you might think there's a vertical asymptote at negative 3. However, when you look at that numerator, it factors to x plus 3 times x minus 3. Yeah, and then x plus 3 over x plus 3 is a foo-foo, and we're just left with x minus 3. And what does the graph of x minus 3 look like? It's a line, no vertical asymptote, a slanty line, yes. That's mx plus b, right? 1x minus 3. So it's a line that has a slope of 1 and y-intercept of negative 3. So we plot negative 3, and then have a slope of 1, and I draw this line. The only thing I have to be careful of is that the function that they gave me wasn't x minus 3. If they wanted me to graph x minus 3, they would have said graph f of x equals x minus 3. But they said graph f of x equals x squared minus 9 over x minus 3, x plus 3. So the only difference, right, between x squared plus 9 over x plus 3, these are equal. These two functions are equal, except for what value? Thank you. Okay, so those two expressions are equal, except for what value of x? Negative 3. I cannot put a negative 3 into the left side. But on the right side, I would get negative 6, right? I would get negative 3, negative 6. Which means I drew this picture. Oh, not bad. Okay. So in this one, x can't be negative 3. And this is the one they asked me to graph. So this expression is exactly the same as this expression, except this one you can't put in a negative 3. So I put a hole. I go negative 3, I go down to my graph, which is supposed to cross at negative 6, and I put a hole. And that's it. So I say these two expressions have exactly the same graph because they are exactly the same, except for that one point, except for 3. I can't put a 3 into that one, so I have to put a hole. X squared minus 9 over x plus 3. Mm-hmm. Yep, that was the given function. Yeah. So that's a rational function whose graph is a line. No vertical asymptotes, even though it had a place where the denominator equaled 0. The reason it's not an asymptote is because the numerator also equaled 0 there. All right, so here's our conclusions about vertical asymptotes. X values that make the denominator equal to 0 could result in a vertical asymptote or a hole in the graph. You get a vertical asymptote if the x value makes the denominator, but not the numerator, equal to 0. And you get a hole if that x value makes both the denominator and the numerator equal to 0. Does what mean? Yes, yes. So in terms of factors, you're thinking in terms of factors. You have the same factor on the top and the bottom. Yep. So the x value that makes this denominator right here 0 is -3. So if I plug a -3 into the denominator, I get 0. But plugging a -3 into the numerator also makes the numerator 0. No, the whole thing, because this factor is 0, and then 0 times anything is 0. Okay. It's okay. All right, so another thing we talked about last class was the end behavior of a rational function. And it often results in something called a horizontal asymptote, but not always. So let's analyze the end behavior of these three rational functions. We'll develop some conclusions. So let's start with 9x squared over 3x squared plus 1. Now, think about what's going to happen to the value of this whole fraction when you plug in ginormous values of x, like 1,000,000, like 1,000,000,000,000, right? Is this plus 1 going to make much of a difference? It's hardly going to make any difference at all, right? If I'm plugging in a quadrillion, think about it in terms of money, right? If I have a quadrillion dollars and Jeff has a quadrillion dollars plus one more dollar, you could say we're basically equal, right? So what I could say is that for x is really big, this is almost the same thing as 9x squared over 3x squared, which reduces to what? Just 3. The x squareds cancel, and 9 over 3 is 3. So this would reduce to 3. So that's my end behavior. That's what happens to the y values as the x values get really, really big. Right, because as the x values get really, really big, that 1 doesn't matter. So I just have to look at the leading terms, and they're going to approach 3. And you can see it in the graph that my y values are approaching an asymptote of 3. So let's fill in the notation here. This says as x approaches infinity, f of x approaches 3. And as x approaches negative infinity, f of x approaches 3 again. And that's because when you square a number, even though we're plugging in big negative numbers, when you square negatives, you get positives. All right, so what was special about this one is that the degree of the numerator and the degree of the denominator were the same. So I was able to just cancel all the x's, right? And all I was left with was the 9 over the 3. All right, let's look at this one where the degrees are not the same. So let's think again about what happens as x gets really, really, really big, right? If I have 9 times a gajillion, right, divided by 3 times a gajillion squared plus 1. Is the plus 1 going to make much of a difference? No. So I could say for x's that are really big, this is approximately the same as 9x over 3x squared. I can drop the 1. It doesn't make a big difference. So now what can I do? Yeah, so I can cancel one of my x's. Right, and what happens to 3 over x as x gets really, really, really big? It becomes very small, yeah. When denominators get bigger, the value of a fraction gets smaller. So this approaches 0. And then when you look at the graph, we do have a horizontal asymptote at 0. You can see the graph is heading down towards it and coming up towards 0 when you look at the far right and the far left. So as x approaches infinity, f of x approaches 0. And as x approaches negative infinity, f of x approaches 0. So in the case, the reason that this went to 0 is because the degree in the denominator was bigger than the numerator. So when I canceled, I still had an x in the denominator that was getting big. So far we have 2 cases. Degree is the same, denominator degree bigger than the numerator degree. Now, if I look at a case where the degree of the numerator is bigger than the degree of the denominator, very similar kind of argument here. Ignore the plus 1. So for x's that are really big, this is approximately the same as 9x cubed over 3x squared. which simplifies to 3x. And as x gets really big, what happens to 3x? It gets even bigger, right? And as x gets really big negatively, what happens to 3x? Gets bigger negatively. So as x approaches infinity, f of x approaches infinity. And as x approaches negative infinity, f of x approaches negative infinity. And you can see that that's what's happening in the graph. So in this case, we have no asymptote. It just grows and decays without bound. Yes. One or none. Yep. Yeah, that's a good question. You can only have one horizontal asymptote at most. It does. Yeah. There we go. I wasn't sure if you would agree with me that it was fun. All right, so for finding vertical asymptotes, we had 3 cases. These were our 3 examples. We have 3 cases. If the degree of the numerator is less than the degree of the denominator, that was the middle case here. The degree of the numerator is less than that of the denominator, our asymptote is at 0. Because you're going to end up, after you cancel, you're going to end up with some x's in the bottom. They're going to grow really big, and your fraction is going to get small. So when the degree of the numerator is less than the denominator, y equals 0 is your horizontal asymptote. That is the x-axis. If the degree of the numerator equals the degree of the denominator, that is this first case here, the degrees were equal, then y equals a over b is the horizontal asymptote, and a is the leading coefficient of the numerator, and b is the leading coefficient of the denominator. So in this case, it was y equals 9 over 3, which is 3. So you just have to look at the ratio of the leading coefficients if the degrees are the same. And then last case, if the degree of the numerator is bigger than the degree of the denominator, no horizontal asymptote, because it's going to just grow and decay to the right and to the left. All right, some fun facts about horizontal and vertical asymptotes. A rational function may have several vertical asymptotes, but it can have at most one horizontal asymptote. And although a graph can never intersect a vertical asymptote, it may cross a horizontal asymptote. What's on the previous page? Oh, yeah, and there's one here too. This B. You can see that the end behavior approaches the asymptote, but it crosses the line right there. Yeah. So horizontal asymptotes only govern end behavior. In the middle of the graph, you might cross the asymptote. Yes. Yes. Yeah. Yesterday, I was putting the asymptotes. I would only draw them to the far right and the far left. I should have done that over here too. Just the far right and the far left. All right, so here are the steps to graphing a rational function. If it's not just a transformation of 1 over x or 1 over x squared, because we did those last class. If you could just, you know what 1 over x and 1 over x squared looks like, so if you can just shift those around, you can go ahead and do that. But if it is not, if you can't do that, here are your steps. Make sure the rational function is fully reduced. That is, factor and cancel anything that you can before you start. Check for symmetry. So if f of negative x equals f of x, you have y-axis symmetry. And if f of negative x equals negative f of x, you have origin symmetry. Find the y-intercept by plugging in 0. Find the x-intercepts by setting the numerator to 0 and solving. Why do I only have to set the numerator equal to 0 to get the x-intercepts? The y is 0, right? So if I have p of x, right? So if this is really what you do when you want to find the zeros of any function. is you set it equal to 0 and solve it, right? But I only have to set the numerator equal to 0 because you can either think of it as you really set the whole thing to 0 and then multiplied both sides by q of x, but q of x times 0 is 0, so the right side doesn't change. Or you can say, well, the only way a fraction can be 0 is if its numerator is 0. Right? So the only way that you can have this fraction p of x over q of x equals 0 is if p of x is 0. It doesn't matter what the denominator is. If the numerator is 0, the whole value of the fraction is 0. Okay, so find x-intercepts. Step 5, find vertical asymptotes by setting the denominator equal to 0 and solving. And because we already reduced in step 1, you're not going to be led astray here finding what's really a whole, right? If you already factor and cancel, everything's fully reduced. Now any place you have 0 in the denominator will be a vertical asymptote. Find the horizontal asymptote, if there is one, using the 3 possibilities we just talked about. Plot at least one point in between and beyond each x-intercept and vertical asymptote, so plot some points, and then connect the points using the asymptotes and symmetry as a guide. All right, so let's do one together. So step 1, we'll just write out all the steps over here. Make sure your fraction is fully reduced. Can I factor anything in there? I could factor the denominator, so I've got 2x squared over x plus 3, x minus 3. Do I have any foo-foos? No, can't cancel. So this is fully reduced. Okay. Step 2, check for symmetry. Okay, so to check for symmetry, I plug negative x in. I evaluate f of negative x. If it comes out exactly the same as f of x, I have y-axis symmetry. And if it comes out the exact opposite of f of x, I have origin symmetry. So if I plug in a negative x here, I get 2 times negative x squared divided by negative x squared minus 9. What is negative x quantity squared? It's positive x squared, because when you take a negative and square it, you get a positive. So this is 2x squared divided by x squared minus 9, which is the same as my original function. So I plugged in negative x, I got the original function back. I have y-axis symmetry. All right, let's see. Step 3, y-intercept. And you get that by plugging 0 into the function. Take f of 0, which in this case would be 0. 0 over negative 9, which is 0. Step 4 is x-intercepts. You just set the numerator to 0, and that we would solve and get x equals 0. All right, let's see. Step 5, vertical asymptotes. Set the denominator equal to 0 and solve. So I've got x plus 3 times x minus 3 equals 0. And we end up with x equals plus or minus 3 as my vertical asymptotes. All right, 6 is the horizontal asymptote. So compare the degrees of the numerator and the denominator. How are they related? They are the same. And when they are the same, the horizontal asymptote is just the ratio of the leading coefficients. So in this case, it would be 2 over 1. So let's see, I'll put that over here. Step 6, horizontal asymptote y equals 2 over 1, or just 2. I should have labeled number 5. These are my vertical asymptotes. All right, and then step 7, plot some points in between your x-intercepts and your asymptotes. So I'm going to start drawing my graph now. I have vertical asymptotes at +3. So I put a vertical line here, dotted vertical line, and -3. I have an x-intercept / y-intercept at 0. So it's going to go through the origin, yep. At 2, so I'm going to put that only on the far ends for end behavior. All right, now we have to plot some additional points in every interval where I don't know something, right? So I want to plot some points to the right of my asymptote, in between my asymptote and my 0, in between my 0 and my other asymptote, and to the left of my leftmost asymptote. So I have 4 regions I need to plot some points. Yeah, so let's plug in, let's plug in 5, right? Anything to the right. And I'm actually going to bring this in a little bit. Okay, so if I plug in a 5 into my original function, 2x² over x² minus 9, I get 50 over 25 minus 9 is 16. What's 16 into 50? 25/8, 3 2/3. Sure. So somewhere between 3 and 4. So 5, somewhere between 3 and 4, I have a point. And then I use my asymptotes as a guide, right? I know that my graph likes to hug the asymptotes. So when I go to the right, it's going to come down towards the end behavior. And when I move to the left, it's going to approach my asymptote. All right, so now choose a value between 0 and 3. One, not 0, because I already know the value at 0, right? But something between 0 and the asymptote at 3. So like a 1, if I plug a 1 into this function, I get 2 over -8, right, which is -1/4. So if I plug a 1 in here, I have a point just below 0. And what if I plug a -1 into that function? Wow, fantastic. I don't have to do anything to the left of the y-axis because I know I have symmetry. So I have a 0 here, and I know this point, so I know it's heading down, so it's got to approach my asymptote. So this is going to go like that. And I don't have to do any more test points because I know I have symmetry. So I can just copy the right side, mirror it on the left side of the axis. So this is going to go like this. And then I'm going to have -5, somewhere between 3 and 4, and approaching the asymptotes. So there's my graph. No. All right, let's use a graphing calculator to just confirm what our graph looks like. Okay, so it was 2x² divided by x² minus 9. And the window I'm using here is like -10 to 10, -10 to 10. And there's my graph. Looks just like the picture we drew. It even has what looks like the vertical asymptotes. It looks like it's drawing them. But really, this is just a glitch in your graphing calculator. It is attempting to connect the lowest point to the highest point because it doesn't get discontinuities. unless if you change the mode to dot mode, instead of connected, use dot mode and then graph it. Then it graphs, but you get dots. And it leaves out the asymptotes. Yeah, it's kind of nice to have it graph the lines because it reminds you that those are asymptotes. Yeah. All right, so let's do another one for some practice. 4x over x squared minus 1. All right, step 1. Make sure it's reduced. When I factor this, I'm going to get 4x over x plus 1, x minus 1. Any foo-foos? Nope, so it's already reduced. Okay, step 2. What was step 2? I can't remember. Symmetry? Yep. All right, so I take f of negative x. I got to plug a negative x in here, and I get 4 times negative x over negative x squared minus 1. This is negative 4x over x squared minus 1. Is that exactly the same as the original function? It is the opposite of the original function. Because you can, when you have a fraction, you can put a negative sign in the numerator and the denominator or out front. So I could write this as negative 4x over x squared minus 1, which is the negative of my original function. So when I plugged in a negative x, I got exactly negative f of x. That means I have origin symmetry. All right, step 3 was y-intercept. So I just plug in a 0 here. 0 over negative 1, which is not undefined. It is 0. You only get undefined when your denominator is 0. Okay, so step 4, x-intercepts. You get those when the numerator is 0. So when x is 0. Step 5, vertical asymptotes. Those happen when the denominator equals 0. And that happens at what values of x? Plus or minus 1. Step 6, horizontal asymptote. We have to compare the degree of the numerator and the denominator. The denominator is bigger, so where am I going to have an asymptote? Yes, and it's at 0. Yeah. Because even if you can't remember the rules, you can just reason it through, right? When x is really, really big, that minus 1 means nothing. And then you just reduce. So this would end up as 4 over x. And when x is really big, 4 over x is really small. So my horizontal asymptote is going to be at y equals 0, which is the x-axis. Yep. All right, and then 7 was plot some points, right? So we'll do that last, after I draw in what I have. So let's see, y-intercept 0, x-intercept at 0, so I have the origin. And then vertical asymptotes at plus and minus 1. Put in some dashed lines. And a horizontal asymptote at y equals 0, that's the x-axis. Now I have to plot some points on either side and in between any asymptote or x-intercept. So pick any point to the right of the rightmost asymptote and plug it into the equation. What do you want to plug in? 2. Okay. So if I plug in a 2, I get 8 in the numerator and 3 in the denominator. 8/3 is almost 3. So I'm going to have 2 comma almost 3. And now that I know that the point is there, Now I know that my graph is just going to approach my asymptotes on either side. All right, now I need a point between 0 and 1. A half, sure. So if I plug in a half, in my numerator I get 2, and in my denominator I get a fourth minus 1 is negative 3/4. 2 divided by negative 3/4. Two divided by negative 0.75. Negative 2 2/3. Almost negative 3. So when x is a half, I get almost negative 3, like that. Yeah. But opposite, right? Yeah, now we have origin symmetry, so I don't have to do any more test points, right? So I know my graph has to go through 0, 0, and a half, negative 2 2/3. And from there, it's going to approach my asymptote. Right. And then I have origin symmetry, which, yeah, which means it's going to kind of do the opposite. And if you can't visualize it, just plot a few more points, right? If you plug in a negative a half, you're going to get almost 3, and your graph will look something like this. Yeah, it looks kind of like x cubed near the origin. And then on the other side of my asymptote, if I plug in a negative 2, I'm going to get negative 2 2/3. And then it's just going to approach my asymptotes. Oh, in the calculator? Yeah, let's check it. So 4x divided by x squared minus 1. Yep, perfect. So you might ask, why do we bother graphing these things by hand when we can throw it in the graphing calculator and have the graph in 2 seconds? One of the main reasons is to force you to think about the horizontal asymptote, right? Thinking about what happens when x gets really small, really, really big and really small, right? To the right and to the left, thinking about end behavior, and thinking about the behavior near the vertical asymptote, right? How it shoots up or shoots down at the vertical asymptote. These are the ideas behind calculus. Thinking about what happens as x gets ginormous, and thinking about what happens as x approaches a particular value. Those are called limits, and they're like the foundation of calculus. So this is sort of the first way we make you think about it. All right, so now I have an activity for you to work on. I have a bunch of rational functions. I want you to just go through the 7-step process and graph each of these. When I printed yours, I accidentally bumped the axes down to the next page, so you'll have to flip the page to do the graphing.